So welcome, everyone. So we are very happy that you are here, that we have people connected online, because this means that there is a lot of curiosity and interest to see how science can go from the lab to the companies or to the development of devices and applications. So I want to mention first that this is a activity in the frame of a network that is called ORGAED, Electronic Devices it's a Spanish network del programa Redes. And Marta Mas is also part of this red, and Nuria, and she's also involved in the organization. So the idea of this activity was to bring a spin-off that can inspire you, the young researchers, and to see that there are other paths in your career. And we wanted also to have an established company. This is why we invited Eliatech, is the first speaker. He will be online and he has to leave. This is why we scheduled the program in such a way that after Karsten Walzer will speak, you can pose questions to him and have a discussion because he has to leave. And then in the second block, all the speakers will present.
Hello?
And then, Karsten is there. And then you will have the opportunity, we will open the session for discussion and questions with the rest of the speakers. So I wanted to thank the communication department from the ICMAB, and Amay and Oriol, who is here, and also, a ver, is mi chuleta, Alfonso del Rey, who is also participating in this event today.
So hello, can you hear me?
Yes.
Yeah,
Yes.
but I cannot hear you.
Vale. In the meantime.
Yeah. Bueno, Esther. Sorry, Karsten. Can you hear this? No? Okay, that's.
Vale. Pues I don't have much to say. So I want to thank you all for being here. The speakers, of course, again, because they make possible this event today.
So, sorry, I can hear you.
Now it's okay?
Yeah, perfect.
Okay, so.
Thanks.
So, Karsten, thank you for being here. So I want to make a very, very brief introduction about Karsten, because about the company Eliatech, he will tell himself. So Karsten Walzer is now the head of the Organic Semiconductors Eliatech. So he is the leader of the Organic Semiconductors development and driving from molecular design to the use of organic semiconductors in organic cells since many years. So he has more than 30 years of experience in organic electronics. And before that, after his postdoc, he was working as team leader in the Technical University of Dresden, together with Professor Carl Leo in OLEDs. And he developed, with his team, the first record-breaking white OLEDs. He has a lot of expertise in growth by organic molecular beam epitaxy, in characterization tools, surface science, scan-improved microscopy, and just to mention that he has a PhD degree in physics from the Technical University of Chemnitz. So, Karsten, so thank you very much for being here. So I leave you the time.
Yeah, thank you.
Hi, Karsten, please, if you can share the screen as we did before.
Yes. Can you see it now?
Perfect. Yeah, now we are seeing the last slide in not presentation mode.
Right, so let's jump to begin. Let's begin with the beginning.
Perfect. That's
okay.
Thanks.
Yeah, thank you. Thank you, everyone, for coming. Thank you, Esther, for inviting me to speak here. Yes, it's a pleasure for me to tell you a bit about Eliatech, what we are doing, why we are doing. And it's basically organic photovoltaics in a manner which not many people have chosen, but we go for vacuum processes. So, and we really bridge the full thing from the laboratory where scientists as you at universities are usually working. We have scaled this up to a full volume roll-to-roll production. And I want to share a bit with you what we have done and what Heliatech is. So here you see a typical picture from our fab. There's a big forklifter running around, and you see there are rolls, and on this roll there are on one substrate coil. There we have a big roll where the solar cells are already produced. And if you see then such a roll here is 1.4 meter wide. You see, you have one roll, and there are 3 lanes with solar cells. And what we are doing, that I will show you in a minute. What is it behind? We are a spin-off of the University Dresden and Ulm, so 2 universities, one for the chemistry, one for the physics. We have brought things together in a joint team. Well, we say that we are the technology leader in OPV, be it true or not. At least we are very advanced in that. Approximately 220 people working here, and we are using venture capital from investors. You see the names here: BASF, eCapital, ENGIE, Acton, BNP Paribas in France, European Investment Bank. So a broad list of acceptors, investors, and the company Acton, where Mr. Quandt, who owns also BMW, is one of our main investors. So we have built up a capacity of approximately 2 million square meters per year, which not all are used because there is a cost topic, of course. But you see here some typical views from our factory. Of course, once you do a new thing, you want to patent and protect your knowledge. I think this is something I can really recommend everyone. So we have approximately 90 patent families, which are granted in several countries, in the main countries worldwide. This gives them in total this 450 approximately. And it's mostly about the materials and the stack, what we are putting inside. So that's, of course, the core of the technology, but also the back end. The back end, how you encapsulate things, how you make the thing become a product to achieve the lifetime you need. I think this is also something valuable and also needs such a protection by patents. The product itself is, I think, self-explaining more or less. It is a solar cell foil, which you see here. It comes on a roll, which you can then unwind and put on your surface, and it is self-sticky. So here, like a sticker for the kids. It is self-gluing on a large number of surfaces, which need to be flat. And then you can put it on basically everything. If it's concrete or steel, aluminum, plastic, glass, you can glue it basically on every flat surface. So the idea is to have a very convenient, just a cable, and that's like a standard solar cell then. And so it is intended to be used in buildings. Can be used for retrofitting, can be used on roofs, wherever you like to have that. So that's what we promised the customer. And inside we have basically some core technologies, and one is the organic semiconductor itself. So the organic semiconductors in Heliatech are homemade. So I'm the person who leads the team making these organic semiconductors. Then we have, of course, the quantum chemistry, the full covered the full things from the beginning, do the synthesis, do the stack design in the physics lab, make stack designs and laboratory cells, and have also transferred this, of course, all these things to our upscaling. So the upscaling regards synthesis, which is done externally, regards deposition, which is done internally. And of course, a semiconductor is not working without a back-end encapsulation. So it was a tremendous work to develop back-end and foil technology. So this is a largely underestimated field, where you need to find the right glues, technologies, barrier materials, processes to delicate to make such delicate products, which we have here, and to scale them up. And we have 2 production lines, the so-called Fab 1, our first production line. Some 10 years ago, we established this one with a 300 millimeter size. This was for the first products, and nowadays we are producing on these large machines, which where I've shown you the foils. This is a volume production now, really, when we have a product with up to 1,300 millimeter. So that's that's really large scale, and this is then also the necessity to produce in large scale, because else it cannot become profitable. Yeah. What we need to do, or what we did in the last more than 50 years, was a tight collaboration with partners from academia, university, institutes, as well as companies across Europe, you can say. Also with Barcelona, we have quite some interactions. So you will see later on a picture from that. We do it really national, international. So that's, we collaborate with the best people we can find, basically. Why did we select vacuum? Why did you select vacuum as a medium and not printing? So printing is a reliable, cheap process, and still we go for vacuum. Well, it is ultra high vacuum, base pressure in the production machines 10 to minus 6 millibar. So of course at the university you have 10 to minus 10, 10 to minus 11 millibar. But it's a different challenge to have huge machines which are 10 meters long, 10 meters high, with the same base pressures. Yeah. Why do we select that? And it is the knowledge which came from the past, from semiconductor industry. All semiconductor industry works in vacuum. It is also the experience from OLED industry. All successful OLED producers work in vacuum. So all mobile phones you have with your beautiful OLED displays, they are made in vacuum. They're not printed. There were companies trying to print that, but the vast majority is doing vacuum technology. This was the reason for us to say, well, these people cannot be wrong. That's why we go for that. By the way, we also do structuring by laser scribing. Also, this is done in vacuum, which is a challenge in itself, because you can't blow the dust away. Yeah, you can't blow in a gas stream in vacuum. Also, this has been solved. Yes, and vacuum is, of course, a very convenient environment in laboratory. So in laboratory, we can use small material amounts when you have working with the start of your research. You can just take milligram amounts and still investigate how such materials can be made. And since we are very often talking about donor acceptor systems, where you need 2 kinds of organic semiconductors, sometimes it's called dopant matrix, sometimes donor acceptor, depends on what we're talking about. but very often it needs two materials. And then you can, of course, in printing, you can mix them. We do it by co-evaporation from two different sources, thermally, and then on the substrate achieve mixed films. And here on the right-hand side, well, very typical laboratory system, which we are using here. The photo is from the company Lesker, where we have been buying our machines. And so this is also used in our labs. Vacuum has benefits. It has the highest benefit is the purity. So it's highly pure. And so we can use then materials which do not need side chains. So a donor acceptor system like this molecule here, the famous molecule DCB5T, where we have 5 thiophene in the core and the dicyanovinyl acceptor groups in the middle. This is a acceptor, donor acceptor type molecule, which nowadays is also used pretty much in printed NFA materials. Also, they use this approach, ADA. By the way, patented originally from Heliatech, so it's one of our basic patents. So these materials can be used in ultra-high vacuum, and they do not need extra things which do not have a function in itself. So for the pure electronic function, we do not need a solvatization of side chains. Yeah, so it's just reduce as much as you can. So this is what we did here. We can also stack a lot of these layers on top of each other. That's why I wrote here, ideal for tandem and triple cells. You can make a lot of layers deposition after each other. And also upscaling is done already. So linear sources are up to 2 meter wide are available in OLED industry, especially in Asia and Korea, China, Japan, where this OLED industry is located. These are the upsides of organic photovoltaics in vacuum. There are also some downsides. For instance, we cannot use large molecules because our molecules need to survive a very long heating process. So it's hot and the materials could decompose. So that's a challenge for us. So each technology has its challenges. And I think this is one of the main limitations of vacuum processed OPV. So here's an example of how such molecular structures look like. I can show you this because it's a model molecule where we have been collaborating with the Leibniz Institute of Polymer Science, IPF in Dresden here, where we have a research project with them to study how such molecules arrange on surfaces, how they arrange in the bulk. And you can see it beautiful that these molecules have a very dense packing on surfaces where you have interactions between, for instance, the blue ones here, the nitrogens, and the white ones are the hydrogens. So there are short interactions between these cyano groups and OH groups, and this stabilizes these molecular films and makes them very robust. Yeah, so this is found for many such ADA type molecules where we have these dicyanovinyl acceptor groups in. They have very dense pi electron stacking, which is important for charge transport. So all these benefits are used here. I can show you this molecule because this is not used in production. It is we have better ones for production, but it does perform pretty well. So how do such molecules behave? This is also again a picture from this Leibniz IPF in Dresden, where the colleagues do morphology analysis for us, because as a company we do not have these fancy tools like ellipsometry, which is shown on the top here, or GVAX, where you have X-ray tracing incidence measurements. So these are typical things which a company cannot afford, but which are used in academia. And you see here, for instance, if you take the red curve here, so this is the extinction coefficient of a flat lying molecule if it's flat lying, and if you measure perpendicular to it, so if you then you measure basically no absorption, and this shows you that these molecules are flat lying on the surfaces. So in plane and out of plane plays a big role for the orientation of the molecules. This is where we have been working on pretty much, and can now well-controlled make such films where the molecules are lying flat. So they are lying flat on the substrate, and so the incident light which comes from the top has a lot of interaction because the light wave can interact with the donor acceptor system here nicely. So this is the science behind it. And then technology-wise, we can stack them here. You see we have absorbers for different wavelength ranges, just the Mickey Mouse graphics here to how a tandem cell looks like. We have absorption wavelengths A and absorption wavelengths B, and these absorbers are put into different layers. And of course, you need electrodes, the top electrode and the bottom electrode, needles conversion contacts, and charge transport layers and things like that. And this is what we are stacking here. So in the production, we have approximately like 20 layers on top of each other. And that makes then the full product. And here you see how such a production is working. And we have a vacuum system, which is the gray container here. And there we are unwinding a foil, putting it through the vacuum system and winding it up again. And what happens in between is we deposit different materials. So these gray things here are co-evaporators. So we co-evaporate layer by layer. And after some time of laser structuring inside, of metallization inside, more laser structuring for the metal electrode, and also in situ lamination to protect the things by a protection barrier foil. So what are some achievements? I think what did we achieve in the last time? I think what you see here is a piece of paper which is a very important one. So because it's a IEC certificate, this is the standard test certificate which a photovoltaic product needs to have, IEC 61215. This means our modules we are producing, they have passed all required tests to be classified as a standard photovoltaic module. And what is behind that? It is a test sequence. You see here, each of these boxes here is separate, or each of these lines down here is a separate test, and horizontal are different tests. And just to say a few words, damp heat test, of course, you need to have solar cells which are encapsulated so well that water or moisture cannot go in and destroy the organic electronics. Wet leakage is very important, so you have to be safe against electricity coming out, that the persons around do not get hurt by electric shock. Ignitability is an important test. Does the product burn? So, and all these things have been done, and we can make a tick bar here. And this is now collected in the certificate. And I think there is no other company worldwide which has organic photovoltaics which have shown the full coverage of all required IEC 61215 requirements. So I think that's the biggest achievement last year, to have now such a product at hand where the customer is on the safe side and can use the product nicely. Well, one big topic in a different direction maybe is the question, how much efficiency do you lose when you go from laboratory to the fabrication? So in laboratory, we have typically cells which are in the square millimeter area, here 0.6 square centimeter, for instance. On the fabrication, we have a module. The one module is 2 meters long, yeah, but it contains stripes of individual cells, and each of these cells has 60 square centimeters. So there is or 2 orders of magnitude in between. And you see how typical curves from laboratory sample and production sample. So the blue is laboratory, the red is production sample, where we have taken such a production sample with the same stack as a laboratory, and you see there is a certain loss. There's also some gain. In some cases, the voltage was even a bit better. It depends pretty much on series resistance of the electrodes here. But you see, in general, the curves are quite similar, yeah, and that's I think one of the advantages of vacuum technology is the scalability from small area to large area. I think that's one of the keys. The key benefits we have in these vacuum processes. And here's now another example for latest developments going from one generation of absorbers for the infrared to the next. You see here that the red curve is absorber generation which have in the production at the moment here, making approximately 700 millivolt. And now we have next generation, which has here a very steep absorption spectrum, reducing the voltage losses here and absorbing also further up to 900 nanometer. And this harvests now more than 100 milliwatt extra, so 0.8 volt. So that's the typical case of how such a development looks then in the industry. And this all here is then put into a triple stack device, and you see here, so solar cell with this sum EQE is the pink line here. This is the total external quantum efficiency we are harvesting, but inside there are 3 absorbers which all cover certain parts of the spectrum, and so each part absorber is approximately responsible for something like 200 nanometers. Yeah, and so identifying such materials is the core of our research work, and especially the challenge is to have it so robust that we have a high rate deposition for more than 50 hours possible. Right. Now, time is more or less over. I think I jump over the last foils here just very briefly. We have a very low carbon footprint, below 10 gram per CO2 per kilowatt hour. This is 100 times lower than coal, or also 5 times lower than conventional silicon photovoltaics. Yeah. Let me just finish with a few pictures. Pictures are always nice. You see some examples where we have done roof installations with just industry which makes such roof systems on different materials, on aluminum, on steel, on walls here. This is an installation at Siemens Energy in Germany. This is one where we are very proud of. So this is Samsung Research, the core research center of Samsung, the main building. There we have the facades with our OPP technology. And now for you guys in Barcelona, if you have the chance to go to the harbor, There we have some roofs covered. Why just these roofs? Well, we were looking for example where we can showcase a corrugated roof, so which is not flat, so which is banded and has different challenges also with the weight. So these roofs cannot carry a large weight, and they should be renovated. And we were doing this together with the company COMSA in Barcelona and the Port of Barcelona. They are the owner of the buildings here. And so this is a nice project which we have done also with the EU funding here, so the EU Life program. Yeah, it was a very long collaboration with the colleagues, and COMSA was very thankful for their patience and their cooperativity. It was great time. Some other examples here: Marburg in Germany, just a round container here used as a substrate for our photovoltaics. This one here is a typical industry facade, very boring facade, and you just use it for harvesting energy. This is also done in this live program in Berlin. This is a storage building in Berlin. Oh yeah, a concrete facade, a mill in Germany. This one is in Spain again, where one of their very early projects. Company Acciona here was a partner. Where we covered such a windmill to use surfaces which are there anyway to harvest extra energy. Yeah, also here this RWE biogas plant used, whatever surface it is, as long as it's not standard surface. Standard surfaces are covered with silicon PV, and for unusual things, organic photovoltaics is interesting. Well, that's I'm now already over time. I'm sorry for that. Yeah, I hope it gave you some insight and some benefit for you for listening. Thank you.
Okay. Thank you very much, Karsten. I don't know where to look at. So now the time open for questions, curiosities that you want to make to Karsten in Eliatech. Here, there is one.
Hello, I only wanted to ask you, how small can the molecules be for the thermal evaporation? Because you saw small molecules, but how small?
How small? Well, they have to be in a certain range. We like evaporation temperatures in vacuum between 150 and 250 degrees approximately. And this means you can make it roughly in a molecular weight between 200 and let's say 700, 800 gram per mole. That's somehow the range where we are. So the challenge is we cannot use fancy molecules like Y6, which is coming from the printed organic photovoltaics. This is too large for us. Unfortunately, we cannot evaporate this. But typical molecules, as I've shown you, these disilane vinyl systems or fullerene C60, these are the typical molecules we are using.
Okay, thank you.
Thank you. More questions? Wait.
Good morning. My name is Diego. And first of all, I want to congratulate you because you say that you get the certificate of the standard 61215 because from my knowledge, it's very difficult. It's a standard mainly for silicon, and I think if you get with this technology, I think it's very important. So congratulations. But I wonder about other standards. For example, for flexible standards. I don't know if you have some other details to offer.
Well, I'm not the right person to tell you about standards. We have a department which deals with that. So I'm from the research, I'm from material scientist. Standards, well, we are looking from the customer side. And the customers, in our case, are people who want to buy photovoltaics. And that's why we need to fulfill the photovoltaic standards. Yes, that's why this 6.12.15 is so important, because then you can directly benchmark our products to every other solar cell product, be it silicon, be it 6, be it cadmium telluride, whatever it is. You can benchmark the things as a customer and can say, well, here you have this benefit, here you have that benefit, yeah, or this challenge, that challenge. That's why this standard is so important. There are other standards which we are following, but I think they are not in the key. Of course, we are a ISO 9001 company, thinks that this is clear, but really thinking from the end, thinking from the customer. That's why this one is so much in focus.
Thank you.
Hi, thank you for the presentation. I wonder, because you show at the end some buildings that you put the photovoltaics like 8 years ago. I wonder, like, the efficiency has decreased, or because like silicon solar cells, normally they have to replace, no, after some years. So what's about these organic solar cells with time?
Yeah, I think you're mentioning a very important thing. Each product has a certain lifetime. The guaranteed lifetime of a silicon solar cell is now 20 years. And this guaranteed lifetime means after 20 years, you will have 80% of the initial efficiency. So this means per year, you may lose 1%. Yeah, that's what is the reference value in silicon semiconductors, in silicon photovoltaics. And this is also what we guarantee our customers, just by fulfilling this standard, this IEC standard. So the IEC standard is basically representing this aging in a certain manner. Yeah? So no one can wait 20 years. So this technology does not exist that long. Yeah. So that's why we have to do accelerated lifetime testing, and we have to rely then on these estimations. And for silicon, I can tell you now there are silicon modules out for 30 years, and they still deliver electricity. Not at full capacity, but they still deliver 60, 70, whatever, sometimes 80%. And for our modules, we have delivered the first modules 2014, which is now 10 years ago. They by then did have a starting efficiency of 5%, very low, but it was the very worldwide very first product with that. No, sorry, very second company. There was a company, Konarka, before that, they had 2%, but we were the first to get about 5%. Yeah, sorry. They are still living. So we haven't monitored them to the end, but at least we know from some customers in Southeast Asia, in Singapore, where they are still living after 10 years. In Singapore, if you have been there, hot, humid climate, very fast degradation of electronics. It's somehow survived. That's why we are optimistic that once we can achieve these IEC standards, that we are able to give a guarantee of 20 years. That's what we do for our customers.
Well, thank you for your interesting talk. Impressive from lab to the spin-off company. I'm not in this field, but I would like to know, or you may want to share some experience or good advices for the early stage career researchers, how we can push our theory or research into the market. What are the best approach at the early stage? Well, thank you.
General remarks are always difficult. I think there are some basic things. Protect your knowledge against copying. That's why we have patents. Patents are expensive, but generate a value in itself, because then no one else can steal what you have done in your hard work. Yeah, I think that's one issue, one point. And the other point is thinking from the customer. Thinking from the customer, which problem am I solving? And so very often, and this is a danger for all us scientists. I'm a scientist as well. I've been a long time in academia, so I know both sides. Very often you have solution searches problem. Yeah, so you have something and you look where you can use it. Yeah. In our case here with photovoltaics, it's different. So we were lucky. There is a general need for electricity. That's why the problem was clear. Yeah. But defining initially what is the benefit for the customer, I think that's the key.
Hello. Thank you very much for the interesting presentation. I have 3 questions. The first question is about, so how does your solar cell compare to silicon photovoltaics in terms of efficiency, first of all? And second question is about like the cost reduction. So is there any cost reduction in fabricating this kind of solar cells with respect to silicon solar cells? And the third question is about scalability. So the question is, which is the amount of solar cells that you are able to fabricate, to produce every year? So also to like satisfy the needs of the customers, I mean.
Yeah, very important questions. Let me answer them step by step. Maybe capacity-wise, we are not very limited. I showed you my one of my very early slides. You see here we have enough production capacity, so the machine can make up to 2 million square meters. Which we are not using at the moment. Yeah, so we are far below that in production. Why are we below that? So we produce on foils here. So this coil which you're seeing here is 2 kilometers long, 2.6 kilometers. So this means more than 2,000 square meters are made in one production run. Yeah. That's I think that's about scalability. We have scaled up pretty much. The key challenge is that the photovoltaic market at the moment is very difficult. Yeah. A standard product comes meanwhile from China. Basically, all major European photovoltaic makers have closed down. We are one of the really very last ones who still believe in photovoltaics. In the US, it's different. The US protect their market. They basically produce most of their photovoltaics in the country. And if you're not producing in the country, you're lost. And you have a high tax, high customs barriers for cheap Chinese modules. What happens? The Chinese dump their overcapacity to Europe. Yeah, this is very challenging now, and makes us quite a hard time actually. So that's why efficiency increase is important. That's what you are saying exactly. That's the point. In the lab, we have now efficiencies around something like 13–14%. In the production is 8%. Yeah. The standard silicon module comes with something like 18%, 19%, some or 20%. This means we are more than a factor 2 below what is done with the silicon glass modules. So this means that our product is meaningful only in places where glass modules are no option, where conventional silicon is not an option. Yeah, that's why we look just for such niches where we can go for roofs which cannot carry standard silicon. Yeah, so you have, I think in the end, I showed you some of these examples. For instance, this one here, so where you have a shaped surface, you simply cannot mount just these standard silicon modules. Here, this one is also a shaped surface. It's also not a standard surface. Facades often has aesthetic limitations, and we come with a very homogeneous area coating. So that's some discussion point in facades. We can put it denser or less dense, as you see here. And on these roof systems here, it is these are lightweight buildings here. So these are just very cheap buildings, and for such cheap buildings, they cannot carry the solar cell weight. Yeah, they're just simply too heavy. So we have an area weight of 2 kilograms per square meter, and this glass module is basically 20. So it's a factor of 10 between. So that's the niche where we are. Yeah, so that's what you have to consider.
Only the last question from the chat is, Carsten, how do you incorporate the vacuum step?
Sorry, Esther, I can very badly hear you. My connection is very bad.
It's how do you incorporate vacuum?
I cannot hear you. Sorry, it's sorry, no, I can't hear you. I can.
Okay. Okay, now?
Now it's a bit better, yeah?
Now it's better?
Yes, now it's good.
Okay, now it's working. So the last question, because we are late with the program, but there are many questions for you. Is how you
Sorry, again, I can't hear you.
how do you incorporate
Perfect.
vacuum step in a roll-to-roll process? It's a question from the chat.
Can you
From
repeat that?
someone.
Now I can hear you nicely, but I didn't
Yeah.
hear the first part of the
Okay.
question.
So how do you manage to incorporate a vacuum step in a roll-to-roll process? It's a question from someone online.
Yes. All machines are big vacuum machines. So we have a big vacuum machine. We put the foil inside the vacuum machine. And inside this machine, we are rolling, we are unwinding everything, we are coating everything, and are winding up again. So all this is done. The core solar cell is made fully in vacuum inside. Yeah. And only the back end is then outside.
And then to put the rolls outside the vacuum, you open the chamber, or how is that?
No, there is a cassette system. Okay, we have a container basically. You have a big vacuum system where with the machine, and you have a small vacuum system which contains the foil, and then you put this you like the ISS, when the ISS is docking, yeah.
Yeah.
In space, they are just docking one gas-tight system to another gas, and then you just open the shuttle.
Okay. So thank you very much, Carsten. So we
You're
will stop
welcome.
here the questions. I am sure there are more, but we have to cut now. So thank you very much for connecting. It was a pleasure to see you online. So, and see you next time.
Yeah. Thank you as well, and I will stay online and listen a bit.
So the next speaker is Alara. You're there. But I don't know if your talk was put in, you sent to Oriol. So, no? So then maybe we switch. Yeah, is it one? Okay, then Adara is here. Okay, maybe you can use this because the other one is not using. Okay, sorry. It's not here then. Yeah, then maybe we jump to Claudia. Okay. Can we do it first? Yes. Claro. Bueno, la presentación. Claudia from Graphenica Lab. You may know her because she was doing the PhD here in the ICMAB.
Nobody was here, I think.
Yes.
Oh no, I see some young people.
Yes, we in the group of Marta in 2011, long time ago, and now she is the Chief Operating Officer in Graphenica Lab, and she will tell about this, about his. So, sure.
Okay. Thank you.
Yeah, remember that the questions, I mean, keep your questions and curiosities because at the end, you will have the opportunity to discuss with all of them.
Okay, for sure. Okay. So thank you very much for the invitation, first of all, Martha and Esther. And today I will explain you a bit about Graphenica Lab as a startup company from ICN2 actually, and how we are working on printed technologies on a way to use graphene as a functional material. Right? Is this working? Yes, no? Okay. Okay. So I will not speak a lot of science, and I will explain more about how the company is structured, the vision, and so on. Okay, and then, but of course, if you have any question, just let us know. So graphene is became quite a famous functional material, and in 2004, right? And actually, it really has really interesting properties, and the ones that we are really interested in printed technologies are because it's really mechanical and chemically stable, and it's multifunctional, so it has optical properties, electrical properties, and it can be functionalized. And it's a 2D material, so this high surface aspect ratio is quite important for some applications. And most importantly, it's an abundant material. And as you know, there are very big problems with critical raw materials. And so we have to make an effort to use abundant materials. There are different types and sources. The most, let's say, pristine graphene that comes from more physical fabrication techniques. You know, it's more complicated to manipulate. It's more expensive to grow. You need a clean room. And of course, you also have the excellent electronic properties as well. And then you have a lot of options on the graphene-based solutions comes from exfoliation processes. And it's really a very big portfolio of commercially available materials already in tons and kilos and whatever you want to buy. And so it is like you can fabricate it in quite mildly fabrication techniques, and it's quite cost effective. And most importantly, it's stable on the and on normal ambient. So it has a simple manipulation. And again, it is quite versatile for functionalization, also because it has more defectivities, perhaps. So in this side, so a lot of graphene inks have been developed, and this is very important because you can create thin film surfaces coated with these materials. And if you have a certain pattern, you can even create solid state devices with certain electronic properties. And these kind of inks have been formulated for different printing techniques. So if we can also discuss this a bit later, better, but each, and I will show you later, each printing technology will need a different type of ink, being in particle size or in viscosity, for example, but to create these patterns and then create multi-layer devices, fully printed or partial printed. And then there is a lot of things done already on conventional printing, which is more like analog mass printing or digital printing, like inkjet or spray coating. Yes? Oh. And there is also a lot of things on 3D printing with these materials. There are a lot of applications published already. There is a lot of commercial links available that you can buy, but actually it's not so easy to create devices with the graphene inks. Just if you buy inks and you test them, I had done this in my career, it will just look like a carbon ink. Because in fact, you need some kind of a structure in your printed graphene device. And this is where Graphenica Lab came in with a patent on itself. And that it's based on a printing process and printing methodology that it's using, and actually it's formulating. So it's actually the printing process, and so you need a specific ink formulations for that printing process. But with that printing process, we can actually control really well the type of graphene structure. We are starting from our reduced graphene oxide, so water-based inks, but I will explain this later. But we can really get the type of devices that have graphene-like properties in not so much carbon-like properties, which is a bit what you'll get if you just buy some ink and you try to coat the substrate with it, okay? So what we do is we really design and prepare inks and printed devices and prototypes for custom applications. And what we are, why we are doing, we think that we can create revolutionary tools for medical, industrial, and bio applications, okay, with this kind of methodology. So it's a bit different from the company before that was clearly already on a stage of a product, product level. We have this product, and what we are here, it's really about a technology still, and manufacturing technology that is able to upscale and create graphene-based devices. So we are really dealing with all kinds of graphene water-based solutions that we can get. We are also functionalizing them to then have for certain applications that I can explain later. And then it's a wax printing step. We have a wax printing mask that we create. And with these inks, we deposit on the mask, and then we use a transfer printing step onto any kind of substrate, actually. So we have been developing several ink formulations for different applications. I will explain later. we are also combining our printing step also in gold sputtered electrodes that you sometimes need as a transducer. It has to be a gold electrode. It's also compatible with post-processing like etching and so on for certain resolutions that you may need. But we are also using we're boosting a lot this part of complementing our printing step as a part inside also other more low cost and large area printing methodologies like inkjet and screen printing because for point of care applications, for example, it is more convenient because of cost efficiency. So basically, we are with our methodology, what we get from our graphene layers is the stability. For example, I don't know if you ever tried printed electronic sensors, but okay, it's a coating, no, it's a soft coating on a substrate. So if you scratch it, it kind of remove. But for example, with certain devices that we have, we put it onto the tip sonicator for 3 days, and it's there still. So for example, with others, it comes out after 10 minutes, and with others, 2 seconds. So it really depends on the type of the starting material, the starting ink, and what type of device we want to do, because then we will also control thickness and porosity, okay, which is very important for sensing applications. So if you need higher capacitance, lower capacitance, if you want to act like a pre-concentration step or not. And so with our methodology, we can control all of these characteristics of the graphene layer. And so then we can develop the applications that we have been working on. Okay, so just for an overview of printing technologies, we consider that we are one more. Usually we are more like in a value chain, we are a component provider of graphene, okay? So if there is somebody doing graphene devices or printed electronic devices, we can offer them the opportunity to create a graphene component in their circuit, for example. And actually we are compatible with all kinds of technologies, as I said before, also with the sputtering and so on. And we can compare fairly normal to any other printed technology. It's a transfer printing step using an analogic mask, which is a wax membrane, okay? So there is all the methodologies have their pros and cons, and what also, how is called, Mr. Rosberg, Karsten, no? Also was explaining, so everybody has its pros and cons, and you need to find your niche market. So basically, but one of our best things is that we are really quite sustainable in the sense we are using carbon-based materials. Usually we try to avoid any other stuff that it's really not needed. And then it's water-based inks. So there are no solvents, organic solvents, let's say. And there is a low setup cost. It's really easy to make or integrate in a bigger line, these wax printing and transfer printing methods. And it's quite cost effective because of that, basically, okay? So we are basically a R&D technology-based company. We have technologies from tier 5 to 7. Of course, we start in 3, actually. And our main business model is by business-to-business licensing. So as I said before, we have our methodology to create devices, and we are more focused on integrating on somebody else that is doing integrated systems in a component from our markets. And this is something also important that Karsten also mentioned, which is choose your market, okay, to develop the product fit application. And so what we have been using, so this is what you can also say, use cases that you can demonstrate your technology to be fit to those markets. We have been, this is what we have more validated in a higher TRL, which for the electric vehicle car industry, battery monitoring systems, okay, because our temperature probes are really good. And then in healthcare, medical devices and biodiagnostics, also for water domain, we have analytical probe that I will also show you. And for aerospatial coatings, well, I don't know if you know that Arabia Saudi's helicopters need to be coated with graphene. But again, that is not so much our main focus because, as I said, we are best on the solid state device because of the control of the morphology of the graphene. So when you look into, okay, I have an application, let's choose a market. And if we look into sensor market, which are a bit where we are going on, there are really big numbers and so on. This is not good because if it's really big, there are big players already there and you don't have any chance that it's everything done. So you really need to go to the niche application, like Carson was saying, and they have like, so our niche application was like in the electric vehicle battery. So here is the numbers for the growth and for the value and water sensors and biosensor, let's say. And you see, it's okay, it's big, perhaps too, but it's also smaller. And so being smaller, it's what where you going for the niche application. So there is a very good dimension of the value of the market that leads us to good applications that you can choose. More importantly for the sensors is that sensors already have a lot of sensors. Okay, so let's say water domain or medical devices already have a lot of sensors, for example. So it's kind of easy for them to adopt new technologies. Okay, so if it's more a conventional that you don't usually have sensors or devices in the sector, it's a bit more complicated to enter, no, with new ideas and technologies. So it's also something important to take in mind. So just an overview of the Graphenica Lab and the use cases. So we have been operating for a long time already. There was a big stop in the COVID, and there is been a renovation also of the administration after that. So we are an innovation-driven company. So basically, we are dealing with a lot of we have like public projects that we can collaborate also, and it's very important for us still to collaborate both with universities and research institutes, and also to collaborate directly with companies for the search of end users that can use our devices. So we have all these kind of this is the public funded projects and the most relevant private projects that in the end where this is a bit more visual to see where we have been, we are much more further is on temperature sensors that we have been making pilot trials with a company because the graphene-based temperature sensor, it's really good in behavior, low hysteresis, and so on. And it's completely printed and seamless, so it's very important actually advancement. And on the chemical sensors for water domain, we are also entering a pilot validation to achieve a TRL 7, which is just prior for certification if we can go through. So this is a bit on the battery temperature sensor, the kind of monitoring that we've been doing with a company here in Barcelona, and we already knew that the sensors was already fairly known validation, and there is a problem only with the connections that we still need to develop. And this is a bit just a use case too. It is a lower TRL. This should be a 5, but it's actually a bit lower. And it's just a project that finished, and that we have been wiring up our graphene-based devices. These were developed for temperature, pH, and heavy metal ions from, how do you say this? Lead, lead, cadmium, and mercury. And we have done the appropriate functionalization of the starting inks to be able to have these sensing. And so we wire up so we complement our devices with wiring up with screen printed electrodes and circuit, which is a bit what it looks like here in blue is actually the whole dielectric coating. And we actually have, this is the whole multiparametric probe that you can see. And it has this little structure of fluidic chamber that it's able to work as for them to be integrated with the electronics for automatic sampling and calibration. And this idea for using printed circuits, screen printed circuit with carbon ink, with basic carbon ink and silver nanoparticle ink, is to create a low cost sensor probe because and to be lightweight and to and so you can reduce costs, so you can make more and you can reduce environmental impact because it is very compact, it's quite lightweight, and you can integrate in different places for monitoring, and most importantly, to install a lot. Because one of the things that this is more for environmental monitoring that you kind of need, it's related to the prediction of and to understanding the heavy metal ions distribution in the environment. So actually, with if you have more resolution, so more sensors, you will be able to also contribute to the scientists that are controlling this kind of events. So this is a bit the two use cases I wanted to show you. I don't know if I am good on time or not. I think it's okay. And so basically, these two use cases have been validated. We have been comparing to, for example, to the gold standard in the EV. We were better even than on the in lifetime measuring on the long run, and of course the cost reduction and that it's also related to installation costs. And then on chemical sensors, we have a weight reduction on 25 times to normal probes that are used already, and also a cost reduction. This is for this case. Other cases, it's much bigger for water domain sensors. And so we have to thank our partners to whom we deal on daily projects, but also to thank you also. And this is a summary. Thank you, and also the funding of the national project, also as an international. Thank you. Questions later, no?
Later. Okay, discussion. And now we pass to Adara. Presentation is there, right? It's there. So now we pass to Adara Babuji, who you probably know her because she was doing a PhD recently in the ICMAB just a few years ago. She finished the PhD, in fact, in my group. So she has a lot of expertise in the growth of organic thin films and characterization by different techniques. And she's now process developer scientist in IdeaDead. I have it.
Yeah.
Okay, thank you, Esther, for the introduction. And yeah, I'm representing Idiadad, and I'm happy to be here explaining about our company and our journey into this industry. So, of developing the next generation of everyday electronics based on new advanced node architectures with non-silicon based semiconductor materials. So, I would like to start talking about the global semiconductor market. And this is a data reported by Semiconductor Industry Association last year, and it shows increasing demand or the sales, global semiconductor sales over the last couple of decades. And it predicts also $650 billion sales for the year of 2025. And here it shows the research and development expenditure for US headquarters semiconductor companies from 2001 to 2023. And here also you can see increase in the trend, which means that a lot of investment is happening in the field. But if you look at the numbers closely, what you can see is that about 10% of the total revenue is being invested back into the research and development part, which is a huge, along with the fabrication facility expenditure. So not many companies can afford to do that kind of research, because this is the data shows different companies doing semiconductor research for different kind of technologies. And when the technology advances, not many companies can afford to do research. And you can see this as an example. When you have a 10 nanometer node technology and below that, only 3 companies can afford to do the research, which are Intel, Samsung, and TSMC. These are the main gigantic companies in the field. So, and these companies are not here in Europe. This is a huge drawback for us, because we have a lot of semiconductor researchers happening all around, but we cannot go to that cutting edge technologies. And if you are looking at the market, Europe's conception of leading edge non-memory semiconductor is expected to be like skyrocket. It's gonna be a lot. When you have a lot of demand and you lack the technology, it's not very economical. So it is very important that Europe should put some effort to be in the industry semiconductor. And how can we overcome this kind of situation is to already start investing in the future technology. So before going into the future, I would like to start talking about the current technology, which is mostly based on silicon. And this graph here shows microprocessor trend data over the past decades. So if you see here, most of the key performance parameters started already saturating. And the one keeps on increasing is the number of transistor per chip. So this is exponentially increasing. Yeah, so what happens when you need a lot of transistor in a chip? You need to decrease the dimension of the transistor. And when you are trying to decrease the dimension of silicon-based transistor, this is what happens. At some point, the mobility of silicon-based transistor gonna drop dramatically, and then it will also, this trend will also saturate. Then, and this is what is happening right now. Right now, we are in material-based scaling era, in which device architecture are being optimized to get better performance. But when you are saturating these techniques, you are forced to go to the next step, which will be heterogeneous scaling era. It's shown here, in which you are forced to use materials beyond silicon. For example, like two-dimensional materials, like shown here, which can have comparable mobilities to that of silicon. And these materials can be incorporated into the already existing silicon-based technology. So the front-end development will not be affected, but you can have incorporate these materials in between, and then you can increase the performance. Also, these materials have more functionalities, which will create or open new innovations and new technologies. to develop. And IDEADIS, as a research and development company, focuses on this aspect of the technology, and we are interested in developing technologies based on this. So how did we start? The company was founded by our CEO, Edward Puig, and CTO, Atsushi Urakawa in 2014, and it started like a small company in Girona. And as time passes, the research group expanded and they moved to Hospitalet de Llobregat in 2018. At that point of time, they were mainly collaborating with academic research groups to lay a strong foundation in silicon-based, non-silicon-based semiconductor researchers, and they were studying the market and how to improve. So there they were trying to develop new prototypes and everything. As the research advances, we needed to have our own research facility to have a high throughput research. And at the end, in 2022, we had our research facility in Villa Decans, and these are some photos of our clean room, which is fully equipped with semiconductor research. I should say this is one of the biggest private semiconductor research facility in the country. So I'll not go to the technical details. I will just try to explain what do we do here. So we have different research teams, they focus on different aspects of semiconductor manufacturing. So we have a process design team. They focus on research on semiconductor material preparation, substrate and wafer preparation, and then they'll also go and develop device fabrication process for process using different techniques, like for deposition, etching, and lithography. So they'll develop all the process for different device architecture. And this device architecture is supposed to design by our design enablement team. So for different functionalities and for different kind of properties, they'll design layouts, this device layout for chips, logics, and circuits. And collaborating with these two teams, we will able to produce new devices with new functionalities, performance, and these devices are being characterized and analyzed to optimize further, to have a fine tuning and to have a final prototype. So this is what we are really doing in our facility right now. And so I would like to conclude about showcasing a positive prospect on European semiconductor market. And this is a data proposed by CA, and it showcases the semiconductor research industrial jobs predicted for the next decade. But last year, European Union has enacted a new Chip Act to promote the semiconductor research in Europe. And this has created a lot more job opportunities and investment in the semiconductor research. So this is where we are focusing on developing promoting our technology. And also for students and people from STEM, it predicts that about 58% of new job opportunities are especially for STEM people and is wide open to the innovation. So in IDEADIS, we are aiming to continue our research on semiconductors based on non-silicon based materials. So this is what we are doing in our facility, and this is what I wanted to share with you. Thank you.
Questions at the end, And the next one will be Luca Pensa, right? It's in the, yes, and let me,
While they're setting that up, just a quick question. What is the profile of the attendees here? Who's a master's student? PhD students, postdocs, full-time researchers, group leaders. Did I miss somebody? Okay, so a lot of postdocs. Good. Okay, I was just curious. Where do you need this? I just realized.
Well, just the short introduction, just to highlight, it was very difficult because your CV is really impressive and broad, and so, but maybe just to highlight that he worked as Director of Technology and Innovation Transfer and Acceleration at IES. This is a business school or in Barcelona. And over the 5 years, he taught more than 150 startups about how to launch, define product market, and grow and exit. And the Barcelona Technology Transfer Group that started in 2016 supported 31 deep tech companies in the early stages and won the Innovation that Inspired Award in 2017. Yes, brief.
Yes,
So thank you.
I still don't know what I want to do with my life, so I keep changing careers. So the most important thing is I'm the least technical person in the room. Mhm.
Right? But now you can talk with concentrate. This is the USB. Open it. It says that it cannot be opened. Basically. No,
Bueno, no, sobrevivimos sin presentación. That's
¿Sí?
one, sí. That's fine. So I'm here to talk to you more about sort of the journey in entrepreneurship in any case. I have great slides which show what we do, but I'm not going to fiddle around with the computer for the next 10 minutes and waste everybody's time. So we are a spin-out of ICN2, of CSIC and UAB. Those are the three academic entities that own our initial patent. So we have a patent license agreement with those three universities. But what I want to talk to you about is a little bit the journey it's taken to get us from laboratory to commercial viability. We are still a pre-revenue company. We're the youngest one, I think, of the group. We turned 3 years old in 4 days. So we are still, I would say, at the initial stages of getting our commercial product out there. So I worked for many years at IES Business School, which is located here in Pedralbes. It's one of the top schools in Europe. And I trained a lot of postdocs and scientists and group leaders on starting companies, including companies like Mitiga, Novameat, Sequencia Biotech. So lots of companies that now have a little bit of traction and maybe some name recognition. And interestingly enough, one of the groups that I trained was, at the time, a project out of ICN2 called Chrome Inc. with Dani Ruiz was the group leader, and Claudio Rossini and Alex Julia. And so they came to a program I was running. We got along really well. They kept coming back for advice on how to start the company and how to spin it out. And eventually I decided to leave my job and join them full-time as the CEO of Distinct. So we rebranded the company, gave it a more commercial-facing name, and then sort of leveraging my contacts and commercial experience, we've been able to, I think, take some pretty big steps quickly. When we started the company, it was important for us to articulate to customers how we did what we did. We spent a lot of the first year explaining nanoparticles. So we are using organic chemistry. We're not a printed electronic, but we do end up sort of in the digital world, and I'll explain to you how. So we use nanochemistry to create particles which respond to near infrared and ultraviolet light. So we can change color under fluorescence because we're using phase change materials. So think of it like a wax. Under UV, you can see our ink, and with the addition of a heat source, basically we use near infrared light, you could use high intensity UV to create a phase change in the material, and it changes color. and then it can revert back. So just a kind of a complex nanochemistry process. And we spent the first year trying to explain to the market how we did what we did. There's a big industry for security inks. The first customer that approached us was the Central Bank of Spain, because on your money, I don't know if you know, or on passports, there's about 14 security features. So this could be inks that are UV inks, near infrared inks. They could be threads, they could be polymers, they could be holograms, there could be microchips. There's lots of technology in just a single banknote or a single passport. And so it was actually the Central Bank of Spain that came to us and was interested in this UV and NIR responsive ink. Now, there's a few challenges of getting onto money, as you can imagine. The first thing that we realized was that we are not an ink. In fact, we are a pigment. And as great as our nanoparticles are, they required a lot of modification and engineering in order to be useful in the industry. And this was a process that took us a long time to figure out and an even longer time to fix. So we kind of spent the first year understanding that, well, we have these amazing nanoparticles, but they have to be protected to get them into inks. And so even learning the vocabulary of talking about ourselves as a pigment within the security printing industry. And then finding we are a completely organic material. We are a water-based solution. So we were built to be green, but when you put our particles into very aggressive ink solutions, they can break down. So the first thing we had to do is protect them with a polymer encapsulation. And not all polymer encapsulation is the same, right? So we were trying to be a green solution for a long time, but it turned out that the best way to protect our particles was with a formaldehyde-based encapsulation process. I think there's other alternatives now open to us, but at the time that was the best alternative. So we had to learn a lot about encapsulation. And so it wasn't just about nanochemistry, then we get into particle engineering. And then once we were able to protect our particles within an ink solution, we had to get it into printers. And we were printing, our particle sizes were about 5 microns at the time, which is fine for screen printing, which is what they use for huge industrial batches. This is old school screen printing, throw the screen down, pour a bunch of ink over it, pick it up, next roll, right? So huge batches, but really not adequate for individual unit printing. So we really needed to get into inkjet. And to get into inkjet, we needed to shrink our particles down to 200 nanometers. So we spent sort of the first, I would say, year understanding this process. We started, in order to get visibility, we started applying or talking to industry publications in security ink. So there was one in particular, Reconnaissance International, which is kind of the leading industry publication for security features. So we were able to present at more technical conferences, one called ODDS, which is focused on technical solutions for document security, printing. When we say security printing, it's basically just passports, money, and tax stamps. So we were able to get on the radar of all these very technical companies and were very successful, and they were the first ones to recognize, I think, the value of our solution in industry. The benefits to them was, if you can imagine a large company like Honeywell or Sun Chemicals, the industry leaders are called SICPA and Crane Next. But these companies, they win government contracts based on the complexity of the security they can provide. So even though we could never sell direct to governments because we are one feature and they had to provide 12 or 13 features, we would be the difference between them winning or losing, or we will be the difference between them winning or losing these bids, because we are probably the highest level of security in the printing industry today with just light. And we're a very inexpensive solution. We are, again, a mostly green solution. So we were getting, and we are continuing to get a lot of traction in that space. The first thing we did, and so I'm going to share the journey of how we decided to commercialize, really, and how the different our go-to-market strategy has changed over time. We quickly understood two things in that first year. The first was we weren't going to go direct to a final customer, right? We were not going to sell a solution to governments, which changes the way you go to market and changes how much money you can expect to make. So that was the first thing. And the second thing we did was look at, okay, what kinds of security feature companies had come out in the last 10 years and how did they exit? Like, how did they end up making money or not? Who did they sell to, either commercially or did they sell the company? And all the references we found pretty much demonstrated to us that single technology solutions basically could generate revenue, annual revenue, about 10 million, 15 million annual recurrent revenue for about 10 years, because that's kind of the life extent of any single technology in the currency market. After 10 years, counterfeiters kind of figure it out, either a way to replicate it or to hack it or to break it, right? And so we were kind of at this inflection point, which was, okay, what is the right market for us? We could do a lot of things with color changing nanoparticles and fluorescence, but what is the right path for us? And then we started, and so we decided that we knew we were not going to be able to raise money on that kind of a market size, right? If you tell investors, and this is my world, I come from kind of more venture capital side and investor side. If you tell an investor, give me $500,000, I'm going to turn it into, a company valued at 10 million. It might sound good to a normal person, but for a venture capitalist, that's not sufficient, right? They want to see more. So we started applying to accelerators. And there was a couple in the United States which were particularly interesting to us. One is a photonics accelerator up in New York, and there was another which was Berkeley Skydeck in California. And they had a history of doing more kind of hardware at the time. Now they're kind of pure AI, but back then they were still kind of doing a hybrid of hardware and software. We were extremely fortunate. By the way, if you want to look at the one in New York, it was called Luminate. So if you're in photonics or optics or photonics, a really great program. But we got into Berkeley Skydeck, which had about a 1% acceptance rate. And we went there with the attitude of trying to find a new business model. We have this great tech, but there's just not a large enough market opportunity. And how do we change that? And the benefit to us of participating in that was they kind of threw a lot of really smart people at us. So most accelerators, the real benefit, or first of all, they gave us cash, which was great. So they invested 145,000 in the company. You won't find a lot of European accelerators that give you cash anymore. A lot of them provide advice and they take equity. But the Americans still give you cash and advice in exchange for equity. So it's a big difference. So they gave us cash, which was great. So I started earning a salary for the first time over a year into the project. But they threw a lot of smart people at you. And all of these smart people had seen over the years, 400, 500 startups. You weren't the first complex technology that they had seen. So they would just ask questions. Can you do this? Can you do that? Why don't you do this? Why don't you do that? Why do you do this? And just bombard you with difficult questions. And we had a month of that where we're sitting in Silicon Valley. We have advisors with all different profiles, from very technical to purely commercial, marketing, et cetera, right? And so over the course of 4 weeks, we radically changed the way we thought about our technology. And that's where we kind of came up with the idea of, we don't want to be a materials provider to others. That's not where we're going to make the most money. I think we've seen 2 other presentations, right? We've all kind of landed on different business models. The first one was all about, yes, we need to build big industrial manufacturing complex. The second is, no, let's license this out to other partners to grow fast. And we're kind of somewhere in between, where we realized we don't need to manufacture at big scale. We're nanoparticles. This is a annual production for me is about the size of this bottle. And I could get onto billions of products with that much pigment, right? I don't need huge production facilities, which means I can keep the manufacturing myself and I can control it, which is good. But we can't possibly reach out to all the customers, right? So we decided we would create encrypted physical identifiers, and that's where we created the idea of printing encrypted QR codes. So we looked at sort of the product market, thought about what is the substrate or the pattern that's most recognizable for products, that's the most common. And we started printing QR codes and UPC codes. Now, in order to create an encrypted solution, we still need today UV and/or near-infrared light in order to change the color of this particle. That limits our marketability, right? We can only be a B2B solution because we need someone with some kind of camera that has a special light source. You can't use it yet with the light of your mobile phone. And so we developed these QR codes and then we started showing people how they worked. And we developed like a mobile phone attachment, which was just a ultraviolet light, which has a low intensity UV light and then a high power pulse, which changes the color of ink. Now, this is where the presentation would be great. It's very pretty and you can see the ink change color and it reverts back over after 3 or 4 seconds. But once we could show it instead of explain it, it was a huge difference. And just the interest of people being like, oh, that's what you're doing. But even then, so we kind of developed this concept through the Berkeley Skydeck Accelerator. It ended in April of last year. We had a new deck, we had a new mission, we had a new vision. It was all about getting onto products and talking to retailers about these really cool QR codes. And we went to market and looked for money and looked for customers. And the market size is tremendous. There's what we call security packaging. The security packaging industry is massive. Mass encoding solutions, which is QR codes and UPC codes, is a huge industry. The EU has new regulation requiring everyone to use QR codes. So it looked like we had picked the right substrate, the right application in the right region, right? So a lot of this is timing. It's just timing and a little bit of luck, right? The difference between success and failure in a startup is a tremendous amount of luck. And we went to market both for investors and for customers. We noticed immediately a much higher level of interest. When you stop talking about nanoparticles, which no one really understands. I mean, if you're not a scientist, what I found was, because I would ask people, when you hear the word nanotechnology, what do you think? The most common answer I would get was, oh, there's these miniature automated robots which are controlled by some sort of central brain and they move around and I'm like, I'm not a scientist and even I know that's not right. And so just, I found myself too often trying to make the technology sound simpler, try to dumb it down for people, right? Which is really hard for us to do. We want, on the one hand, we always thought we were selling complexity. We're doing these incredible things that no one else is able to do. We kept trying to explain how hard it was. And that actually wasn't working. And so when we went the other way, which was, no, nano just means small. Micro, small, nano, smaller, quantum, smallest, right? Just trying to get people's head around what it was that we were actually doing actually gave them a higher level of comfort. Once they didn't think we were controlling inks from some central brain that we could modify whatever's printed on any packaging, which was actually what people thought, it made it easier to build sort of the confidence and trust in what we really wanted to do. So we went to market with this value proposition. We were starting to get traction, but we couldn't, and this is where you make difficult decisions. We eventually would have been fine if we had just stayed on that track, and eventually we would probably have been successful. But we recognized that investors were not putting money just into nano for the sake of nano. I mean, people talk about deep tech all the time, but deep tech is really not as transversal as we would like it to believe. I think that in the technical community, there's a lot that goes into deep tech, but investors are only looking at 2 or 3 technologies in deep tech. Anything that's healthcare, great. Anything that's, AI, great. Quantum computing, great. Anything outside of that scope just struggles to get attention. So we decided that we needed to have a stronger software engagement. And this is when we made the decision to stop using the words nanotechnology. And we made this decision at the end of November and redid the deck and reworked all of our materials. We built wireframes of our app. And in this process, we found out that actually the biggest demand in Europe right now is there's a new regulation around digital product passport. And this is where manufacturers have to demonstrate that they know how all of their products move through a supply chain. So we're leveraging this new regulation. And there's also another regulation called the right of repair for electronics companies. Anyone who manufactures any kind of electronics company has to provide a maintenance and repair service for 10 years. So these 2 regulations, when we started talking to customers, they kept coming up over and over and over again of what are the potential use cases. And since we can encrypt a physically printed QR code, because, and I'll get into how we do it, but we can encrypt these QR codes, then we can actually provide a more of an audit-worthy tracking. So if you can connect that to blockchain, you have a perfectly auditable, verifiable supply chain, which is great for regulators and it's great for end customers. So we realized we needed to do 2 things. One was understand what encryption meant and articulate that to customers. And the second thing was we needed to provide an ink that would react to white light. Because at the end of the day, the real interest was to get to end consumers. We want you with your mobile phone to turn your flashlight on to create a color change effect on a QR code, which we can encrypt. And you have the guarantee that this is real. So I went into a store, actually these shoes. I went into a multi-brand store. I saw these Adidas for $40. And I thought, well, they can't be real. I mean, I doubt they're real, but I have no way of knowing. Wouldn't it be nice if we all had the confidence that what we're buying is real? Fake goods are everywhere now, and they're growing, and they're working their way into like standard supply chains. It's a huge problem. It's medicine, cosmetics, clothing. We think about apparel as the primary victim, but it's not. It's 47% of all brands are being counterfeit. And some of these have massive health effects. And then not to mention the secondary environmental and social impacts of poor labor practice, pollution, et cetera. So we knew we needed to do a white light responsive solution. So we immediately started putting that together. And we've got some early sort of proof of concepts done. But the second thing, and the most important thing, was to understand what encryption meant. So when you develop an encrypted QR code, what we ended up doing was actually working with another startup here, Color Sensing, some of you might know, in basically creating an algorithm which could map and decode our ink. So we've mapped how the phase change materials affect the way we change color under fluorescence. We program that into an algorithm, and that algorithm is able to validate our specific inks because they're only going to change color in a very certain way with certain stimulus. And now putting this entire sort of business concept into practice, we only talk about ourselves now as a software company, which hurts. I mean, we're 5 people full time. 4 of them are material scientists, are nanochemists. All of our founders are nanochemists. And it hurts not to talk about it. But this is kind of the journey that we've been up taking. And now we're talking to primarily Web3 investors, so blockchain and software investors. And those are going to be the ones that ultimately invest in us. And so I think the story I wanted to tell you is just always be listening. And it's very, very hard for, I think, technical people who love what they do to hear what they need to hear when it comes to customers. And even Alex did his master's, his PhD, his postdoc at ICM2. He's been working with this technology forever. I don't think he'll get offended if I say this. I've said it in front of him. You know, when we sit in a conversation with a customer, what he hears and what I hear are different things. And so I think a lot of this is about building your team and getting different disciplines on at the right time. You know, the next 5 people we hire, one is going to be an electrical engineer who can optimize our mobile phone adapter with UV light. The person after that is going to be a software engineer. We're going to need 2 people in computer vision to build out and scale our algorithm. Like, I'm not going to hire any more nanochemists for a long time. Now it's all about bringing in other disciplines with other expertise to help with the other parts of the business. So it all starts here. It all starts here, but this ends up being a lot of the time a really small piece of what turns into commercial success. And so I love what all you guys are doing. If I can ever help anyone with anything, please feel free to reach out. It's a long journey and it takes a lot of curves, and we still haven't sold anything. So it all sounds great today, but I'll come back next year. We'll see how we're doing. Happy to answer questions later. Thank you.
What you take? Yeah, for those online, the previous speaker did not have slides. It's not that you did not see. So now the last one is Alex, also from House, from the ICMAB. So probably you know him also. So he was doing the PhD degree in physics in the Imperial College of London, and after a postdoctoral stage in the ETH Zurich and the ICMAB. In 2022, he came again to the ICMAB to work in these transfer activities in the field of pattern optical security systems. So please tell us about your last adventure.
Thank you very much, Esther. Okay, cats and kittens, let's get started. So I propose to play this slightly differently. What I would like to do is to briefly show you a timeline of our company, just so you get a sense of how a spin-off can be born, conceived, and grow up. And after that, we'll go back to the original place where the ideas came from, and all together just pluck out a few and try to develop them live together into a spin-offable product. So to do this, I'll need to talk very fast, and I will show you lots of pictures, but do me a favor, don't pay attention to the details. In the end, the good stuff is never in the data sets or anything like that. The good stuff is in the transitions between data sets, in the cascade of logic that connects A to B, in the velvety silence between notes, in the margins of a page that the poem never reaches. Okay? Cool. Are you with me? Blink if you're with me. Okay, this is my room now. This is my room. So here we go. In the middle of 2020, Mariano and I published the paper and the patent. And after that, we started making inroads to how to license this technology. And a little bit down the line, Be Able Capital appeared out of nowhere and said that because our paper was published open access, they read it and they're interested in funding a spin-off. So what followed was a grueling months of market research, 10 emails per day saying, hey, we found this Japanese patent. Why is your stuff better than that? Wow. But eventually the company is founded, you go to the notary office, you put your signature, and then the notary asks you, so is this the most exciting day of your life? And Mariano, cool as a cucumber, says, no, third most exciting. I already have 2 kids. Rock and roller. Okay, so the company is founded and soon enough work starts. That's me and Mariano. Okay, and when work starts, you have exactly a year to impress these guys with your technology development, because then you have this exam. And compared to my PhD exam was a shiatsu compared to this. This is real serious stuff. And after you graduate, you hire a CEO, And soon enough, Michele joins us from University of Southern Denmark as a superstar R&D scientist. Michele, can you give a wave to everyone? There she is. Hi. Okay, so of course, all through this time, you need to look for funding, and so we won a few grants here and there. And this is where we are now. So now we know each other, Molecular Gate at your service. Okay, so let's go back to the genesis of this stuff. What got us onto this rocky road? So we love organic molecular electronic materials because they're so adaptable and versatile, okay? So here's a research question for you. How do you pattern everything, meaning composition, microstructure, orientation, in everything, meaning any molecular material you have in your drawer, with everything? So laser, solvent vapor, printing, you name it, okay? And we came up with this platform concept called the molecular gate. So let's make a sample together, okay? You start with a film of polyfluorine, okay? So here you have a schematic and a fluorescence image. In amorphous state, this polymer is deep blue emitting, okay? But it is extremely sensitive to even the most minute exposure to solvents. And when it smells a solvent, it flips into this extended beta phase conformation that you see. I'll just point, okay? Into this extended beta phase conformation that you see there, and it changes the fluorescence color, okay? So on top of this film, we coat the molecular gate interlayer, okay? Just a water-soluble polymer, way less fancy than it sounds. And on top of that, we throw a functional additive, which is in this case a low melting solvent. And you see that the color of emission of PFO is still the same. It doesn't know that 80 nanometers above it is a pile of its favorite solvent. It has no clue because of this interlayer. Until you come with a stimulus. Stimulus can be anything, in this case, solvent vapor. This wakes up the functional additive, slightly opens the gate, and then the additive diffuses through the interlayer, and you print your little beta phase dot, okay? And at the end, you do a lift-off, but I told you that this was a water-soluble polymer, so you just actually rinse your sample under the tap, give it a shake and bake, and then you're done, okay? So this is, the basic concept is basically tracing paper. So now let's do something more useful by making two tweaks. Let's replace the additive with a dopant, and instead of the stimulus, let's use a laser, okay? Green laser, it absorbs in your polymer layer, generates heat, and this is your stimulus. And this, folks, is a way to pattern local doping. So here you see it in the shape of an RFID antenna, okay? And if you calibrate your Raman spectrum as a function of doping level, then you can actually quantify these patterns. And the main thing that buzzes me is that outside of the pattern regions, the conductivity of your film is unchanged. So this is serious full patterning, okay? So applications can be contact doping for OFETs. Now let's do something really wild. So let's make two different additive molecules erase each other. So we start with a blue emitting PFO film. The stimulus is solvent vapor, and then you have two dyes. You have this athletic green dye, the coumarin, and below you see this out of shape orange smoker over there. So let's go. At the beginning, you don't see the emission from the dyes because of concentration quenching. Okay, you're applying your stimulus, and soon enough, your green dye diffuses through the interlayer and down converts your emission to green. So you wait a little bit longer, and soon enough, the orange guy crosses the finish line, just about there. And so this is a way to pattern RGB emitting active layers in one step, just by tweaking the dwell time of your stimulus. Very cool. Okay. The other thing to do, the most complex one, is to pattern molecular orientation. And here, you just have to be a little bit creative with choosing your functional additives. So the mechanism by which it works is kind of like a zipper, okay? So you have two halves. Your small molecule provides a template, the left side of the zipper, okay? So you need it to crystallize out first, so you use hyper-eutectic compositions. It's really not that hard. And then once the left side of the zipper is there, you just need some epitaxial match with the right side of the zipper, and then they click into each other and they orient. And in fact, this is So easy to do that you can do this with a ballpoint pen. So when I said you can use anything as a stimulus, I meant it. There it is. And there's your radial chain orientation. So you can, of course, do this with a laser. I'll skip through a lot of the details. The only thing I'll point out is in this polarized micrograph here, you see that you're scanning your laser from west to east, and this polarized microscopy tells you that your chains orient with the writing direction. Okay, so where's the spin-off here? Well, one way to approach it is to take the most challenging aspect of all of this and develop that. And what we thought we'll do is use this molecular orientation patterning to make polarized level 1 security features, which we call polograms. Polograms, you with me, yeah? Blink if you're with me. It's still my room. Okay. So when I say level 1 security features, I mean, this is the true democratization, okay? These are designed to be accessible to all of you without requiring any fancy gadgets, okay? And because of this, they're the hardest ones to do. For example, this is state of the art. Well, gee, where's the innovation? The holograms and OVIs, this is back from the 80s and 90s. Thermochromics and microprinting, super slow. Nobody will ever use it. And the only cool thing is micro-optics. This is relatively new, but it is extremely expensive and basically limited just to banknotes, okay? So for our hologram security technology to succeed, you have a bunch of pretty difficult challenges to address. The most complex one for an academic mind is this one. And this is basically a mantra that you need to have in a spin-off company. Each processing step doubles the cost. I'll tattoo it on my right shoulder. It's really important, so you have to make things simple, but not too simple that it becomes counterfeitable. And so we learned how to print hologram security features, okay? So they work in see-through and reflective, and I'll just show you some examples here and there. So for see-through holograms, they take advantage, for see-through holograms, they take advantage of the fact that we are surrounded by polarized light sources, okay? This is not a special gadget. So there's a polarized light source there, there, we all have one in our pocket. There's probably another LCD screen somewhere, but you get the idea, yeah? And so instead of printing just something normal on a pack of, on this shrink overwrap, this is a cigarette packet. You can imagine this to be whatever you want. All the members of the audience can think of Viagra. There's no judgment here. This is a product that needs to be genuine, okay? So under ambient light, the hologram appears basically featureless. That's in panel B. And then when you crack it open against an LCD screen, you see the hidden security pattern. And then when you rotate one or the other, the pattern colors shift. And this color shifting is synonymous with optical security features. All of them operate like this. Of course, it works also against a smartphone screen, super ubiquitous polarized light source. And the clear sky actually is a pretty decent polarized light source as well. So this is in reflection. There's lots and lots of application areas. The one that thrills me, because we do this with drop-on-demand inkjet printing, is this one, ID cards. Imagine if there was a hologram in this window. This is where inkjet really shines. You don't need any mask. Every time you print a pattern, it can be a different pattern, like this handsome lady. So this was in transmission, and in reflection, the holograms are invisible under diffuse ambient light. But as soon as you hold them to any direct light source, something like this, you see the security pattern revealed. Okay, so now you see half of something original, and then you rotate your hologram security feature, and it's the Pfizer, and the QR code is shifted colors. So works very, very easily, and they're scannable. These guys need to work super fast. So 2 seconds is all you have to verify, and it's actually, it just works, and it works fast. Okay, so this is one line of research for us, one line of product line. What else can we do? So let's think back to the original ideas. Well, what else can we pull out of there and make this into a product? Well, do you remember earlier when you weren't paying attention? I showed this video here. Aren't you impressed by the color change? I mean, this is huge, from orange to black. It's pretty cool. So let's keep this one on the table, and let's dovetail it with diffusion and multi-layer structures. Okay, and then needs something else. And the final thing is to remember that the melting temperatures of our molecules, they're very easily tunable by substitution. Melting temperatures and diffusion coefficients. And so if you do all of this, you end up with a molecular clock, a molecular phase change clock. So what you see at subambient temperature is this. And then you see also this 2 weeks later, a month later, whatever you want. But as soon as you take it to room temperature or so, the clock starts ticking, tick, 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 tick. And then you see this color change happening from right to left. And all of the colors you see here, there's no chemistry going on. This is just phase change, physical chemistry, the highest branch of chemistry. Okay? So this ticks, ticks, ticks. The video is sped up 40 times because you cannot show a clock ticking in real time. So what is this useful for? Well, actually, folks, this is a time temperature indicator. So these kind of time temperature indicators are used to ship vaccines. And this particular one is used in German hospitals. Pretty cool device, right? Kind of expensive, $5 a unit. So you get this one and you test it. And so you heat one of these. So this one is designed to tick above 32 degrees, right? Let's heat it to 40 and it starts tick, tick, ticking. Nice color change. I like it. Then you heat it to 50 degrees. And here you have to pinch me because are you really telling me that the more you cook your, I don't know, COVID vaccine, the less your indicator knows about it? Huh? This really doesn't add up. It's a terrible device, a device that only a mother could love. But you just spent $5 in it, okay? So we did this project in collaboration with these youngsters from Mariana's group. And when we studied the dynamics of this phase change happening, it's actually fully Arrhenius, unlike that Warmark crap. And the activation energy is actually bang on with what you have for typical mRNA vaccines. So 159 kilojoules mole and about 100 for vaccines. Beautiful. Okay, I will take 60 more seconds to tell you one last thing because it's our latest work and I kind of love it. And it's my show, so I might as well. So I showed you this stuff earlier, patterning doping for contact doping of offsets, whatnot. There's a problem here, which goes back to this thing I said, every processing step doubles the cost. And this unfortunately includes this alignment step. You need to align your laser with your OFET contacts, pain in the ass. So the way to do it properly, well, let's use the transistor contact itself as the heat source. That obviates any need for alignment. And then to use that contact as a heat source, you just connect it to some contacts to Keithley, joule heating, generates the heat. And this just works. This is our kind of latest research line. Here you see 1, 2, 3, 4 electrodes that were heated. And these are our conductivity profiles. And this is our reference electrode that wasn't heated. And nothing happens here. Beautiful stuff. I love it. Okay, so this work was started with Mariano and this gentleman here, Osnat Zapata. Fabulous, fabulous experimentalist. The right amount of flair, the wrong amount of hair. I can say this about him because he's my friend. And then recently, Michele and Martino stepped up and made this stuff work in less than a second, I think 0.6 of a second. So I'll play for you this video now of them doing the contact doping. Don't blink now because you'll miss it. This happens really fast. Puff. There's your first doped contact. So this is where we are now. And at this stage in a spin-off's life, the real challenge is how do you make solutions that are plug and play for mass production in the lab? So this is the real difficult bridge for us to jump, but that's why we're here. We could be in Dresden and it's, but it's better to be shoulder to shoulder with remarkably warm and creative people that we are fortunate to have in this joint. And if you do, yeah, it's nice to have a slot dicoter in vacuum, but then if you're a little bit creative, you can actually take your doctor blade and in one step coat Catalan solar cells. True story. So the red one is PQT12 and the yellow is F8BT, one pass with the blade coater. And with this, on behalf of our little outfit, Mariano, Michele, and Jose, I thank you.
the last one. Hope that you are. Alfonso del Rey is working in ICMAB. In the yeah. So the last speaker is Alfonso del Rey. He is the responsible of the transfer unit in the ICMAB, and he will tell some practical aspects of CSIC, and if you want to patent or you want to go to transfer, he will give you some advice, right?
Okay, thank you, Esther, for the presentation. I will be very brief because I hope that you all have a lot of questions to the other speakers. And well, I will make an introduction on how to create a spin-off in ICMAB. And for those of you who are not ICMABers, just to say that we have in our institute, we have 3 big fields of research, which are energy, electronics, and health. And in ICMAB, we have a knowledge transfer unit since 1997. Nowadays, we are 2 people. In 2 weeks, we will have another technician. I do the kind of job that is usually associated to the knowledge transfer unit. But we also have Gerard in our team. Gerard is in charge of the prototyping lab. This is a new lab that we have here in ICMAB. And in this lab, we try to produce, create the prototypes of our devices, our equipment. And we think that it's very important because it will help us to commercialize this kind of technologies. And obviously, we are a part of CSIC. CSIC is the biggest research institution in Spain. And we have a lot of technicians in our headquarters in Madrid that give us support in things related with protection, spin-off creation, management agreements, management, and so on. And as well, we have a lot of commercialization technicians all around Spain. And well, we share good practices and the knowledge of companies and investors, and that's very helpful for us as well. ICMAB has a guide to create a spin-off. You can find it, all the people that is from ICMAB or CSIC in general, you can find it in the intranet. Probably nobody has seen it before, but yeah, you can find it here. And well, it's very short document, and the main points are the following. First of all, we have a definition of what is CSIC's spin-off. This is not trivial because every institution has a different definition of what is a spin-off. In our case, we consider a spin-off a company that has been created to develop and exploit a technology that is owned by CSIC. And we have a license agreement with this company. There's also the procedure of how researchers have to inform CSIC about this creation. You have to give some information to CSIC. For example, which are the partners, is the technology that you are planning to exploit, if there are investors, which is the business model that you try to develop with the company, and the rules of participation and contribution of researchers to the spin-off. That's you have to have in mind that if the CSIC doesn't participate in the new company, in the spin-off, researchers are allowed to have a maximum of 10% of the shares of the company, and researchers cannot work or participate or have work in the company. Unfortunately, CSIC generally doesn't participate in the companies because it's quite difficult. So normally we have this rule, only 10% of the participation. CSIC, although it doesn't participate in the company, assess the researchers with the partners agreement, all the issues related with the creation of the spin-off. We can also negotiate the license agreement, research agreements with the company. We can help the company to get funding to develop the technology. And CSIC as well can incubate these companies in the institute in the first years of life. And there's as well all the laws that you must consider when you create a spin-off. Well, that's perfect, but in fact, we are talking about this part of the very long process. There is a knowledge transfer project. Obviously, we are going to help you here, and you have to explain us the idea, the project, but probably we already know the project because we are going to work together with you during all this process. Maybe from the very beginning, when you are thinking about apply for a project in a call, and you may think that it would be interesting to have the results are going to be interesting for companies, or maybe you get some results that you think that, well, it might be interesting to have a patent application. So we are going to help you all the way, not just in that moment. Because what we in the knowledge transfer unit, what we are going to do is to help you to get higher readiness levels in all these parameters. Probably most of you know that it's important to have a higher technology readiness level. We have seen in some presentations comments about the technology readiness level. Obviously, we all know that we need funding to get this information, and as well, we know that we need to have patents to protect our technology. But there are other things that are really interesting. Very important if we want to capture the attention of investors and convince them that it's a good idea to invest in our project. We need to develop a team. We need to have the researchers that are involved, other people from ICMAB, to add new skills, and as well to engage people from outside ICMAB to be members of the team. We as well need to know the customers. But not only the customers, we need to know all the stakeholders of the value chain. We need to have all the picture and know where we are. And as well, we need to develop a business model because we need to know what we want to do if we create a spin-off, how we got this funding that we need. And just some comments about our ICMAB activity. In ICMAB, we have created 6 spin-offs. We have 2 pioneers in 2010, which were Nanomol Technologies and Absolutia. And we had to wait till 2020, 10 years, to have the next one. And we have create 4 spin-offs in the last 5 years. This is not a coincidence. This is a consequence of a lot of factors. There are internal factors. For example, in 2016, we get our first Severo Ochoa Award. And ICMAB decided that one of the things that wanted to do was to empower the knowledge transfer unit. And we also make some internal proof of concept projects to develop the technologies that we were getting here. And as well, CSIC has changed the philosophy in relation with the spin-offs. Now, our headquarters in Madrid really encourage researchers to create these companies. And as well, there are external factors. For example, nowadays we have a lot of calls related with knowledge transfer. Normally, they are proof of concept calls. We have them in Catalonia, Spain, and in Europe. For example, here we have an European Innovation Council transition project. And these are really interesting projects, which you can have up to 2.5 million to develop a technology, to create a spin-off or to invigorate this spin-off. And as well, we have some private funding like Cash Research and things like that. And I would like to mention one call from CSIC that is really interesting. Is named Impulsate. Impulsate is focused specifically in the creation of a spin-off. Normally, these kind of projects try to help to develop all these readiness levels, but Impulsate is focused mainly in developing the team, know the customers, make, for example, market studies and things like that, and to develop a business model. And sometimes these kind of things are difficult to make with other conventional proof of concept projects. And well, in the last 4 years, we have started 39 projects like that in ICMAB with a budget that is close to 8 million euros. And we have now 7 active spin-off projects. So for the people from ICMAB, well, that's all I wanted to say. People from ICMAB, if you have some questions or you have an idea about a possible spin-off, just get in contact with me and we will discuss it. Okay, thank you.
See, now it's working? Well, if it's, I hope it's working. If not, the people who are connected online can write if it's not working. So now is the last part, is the open session for questions to the speakers. Maybe the speakers, I mean, we don't have chairs, but maybe you can come here in front. I will ask you to come in front because it's better to answer the questions. So I will remove it. And now we open the session for questions, curiosities to all the speakers of today. Well, you can see it. I know it's not very comfortable. It's cold. Cold, I know.
Hello, thank you for your presentation. So I have a question for Luca. Luca, is that right? Yeah. So, or anyone else really. So you said that you basically spent about 3 years basically looking for the problem, right? So you started with the solution as happens often in science. So so you spent a lot of effort trying to find what is it that actually the customers want. How are you going to use your product? And you yourself said that the actual core technology that you started with is going to be a fraction of what you are actually going to be doing in the end. So I was wondering if this is a common thing that happens. From what I heard, it is quite common. It happens a lot. And why do you think that happens? Wouldn't it be better that you now, after having spent 3 years looking for the problem, now that you came to ICMAB or to ICN2 and say, look, I have this very important problem, who can solve this for me? And I'm sure that in ICN2 and ICMAB, there are several teams and each could come up with an idea of how to solve your problem because you have a very specific question in mind. So I was wondering if you could comment on that, if you think that's normal. Or...
It's a short question, a very long answer. I think part of it is the relationship between spin-outs and spin-out offices, right? This whole concept of tech transfer differs from university to university, country to country. I think you would find a very different support infrastructure. Just the whole way, I'm originally from the US, the whole way someone like MIT, Stanford, Berkeley, the way they're structured as an academic institution is to encourage from a much earlier stage, higher levels of collaboration between technical, commercial people. There's a lot of interactions between business schools and engineers and scientists. So it's a very different picture. One of the reasons we were eager to get into the US for an accelerator was because we could leverage these relationships easier. You can also do it here. UAB is a great institution. It just takes a lot more legwork. So it's very common. I think some people are lucky enough to maybe have a problem come to them and it works earlier and you get to skip a lot of this, but others not. The hard part is to finance these last 3 years, right? It's all of us are a combination of grants, maybe some business angel money. You're not going to get a real investor more or less, I mean, be able is a different beast, but be able is one of a kind. So if they pick you, great. If they don't pick you, what do you do? And so it's a complex answer. I think you have to just fight with what you have. And after I've seen lots of companies, I've seen every scenario what you're asking, right? I've seen companies that have great, clear use cases from their biotech companies, know exactly what they're targeting, so it's easier. But for a lot of us, it's just not like that. It's not a reality. And if the institutions aren't going to fund 3 additional years of development, which would have been ideal, but what happened in reality was the postdoc who wanted to found the company, his grant ran out. So we had to start the company and hire him. Otherwise, the concept never would have been born. And so when you're pushed into these things, you have to do what you have to do. I don't know if anyone else wants to take a crack at that.
I would just add that a startup can do basically the same that we are doing in research institutes, but then there is this little leap which seems, oh, you just go for customers and you try to adapt to that, and in that voyage, then you get to have integration about other technologies than yours. That doesn't mean that you need to go back to research. Probably it's just an engineering problem, like the one I commented in the connectors, for example. Or, as you said, you decided to move on the value chain and not delivering a material, which is in the beginning of the value chain, and go to a more added value product, which is at the end, which is an integrated system. Then you also need other technologies to integrate that. So it's really, you need to be in the industrial ecosystem, in the side of a startup, to have the time, to have the research of your technology to fit the market that you need to be placed, no? And just also another comment that sometimes you're also driven by investors to focus in certain markets, not the one that you thought or you want. And that is also another different thing. So you can choose and more yourself if you go to customers, and if you are more tied to investors, then sometimes you have their own specifications also, like I want to focus in this market, and then you need to go to that market.
So more questions?
I want to thank you all the speakers for the interesting presentations, first of all. I was wondering, I mean, which is the advantage of starting a spin-off within the CSIC with respect to private accelerators? I mean, because as far as I know, the process of licensing within the CSIC, I mean, is not so advantageous because the inventor get only the 30% of the cake.
About that, I can answer, but that is also, if you're hired by CSIC, it's from CSIC. So if you're hired by somebody else, it's also from somebody else, so you cannot change that.
Yeah, well, you mean when you have a license agreement and you have royalties from the company, the shares of these royalties are 1/3, 1/3, 1/3. 1/3 is for CSIC, 1/3 is for the group, and 1/3 is for inventors. The thing is that that's what the science law determines. So we are just doing what the law says. In fact, we did that before the law says that. So we have this kind of share from, I don't know, maybe from 20 years ago. And it's not different from other companies. The thing that sometimes is maybe more difficult for us is the fact that it's quite difficult from CSIC to enter into the company. In ICN2, it's much easier, for example, and that's also gives researchers it's interesting for researchers because they can work for the company, they can be in the board of directors, they can do much things to the with the company that in our case.
Okay.
I just want to add one big bucket of ice cold water for all the researchers who dream of having huge equity and spin out that they don't want to work in. If you are chasing venture capital money, very bad formula. The first question investors ask us after they get through some technical due diligence is, what does your cap table look like? And if I had a cap table that had 40% of the company or 50% of the company owned by full-time researchers who were not going to leave their jobs to work in the company, 0% chance that they invest. The standard for venture capital is full-time employees should have about 75% of the company. So if you have to chase venture capital, which is not always a requirement, a lot of times you can get away with grants and revenue, right? That's ideal. But if you have to chase venture capital, just it can be very difficult if there's a lot of what they call dead equity, which is people who own the company but don't work there every day.
Thank you. Yeah, because this is interesting because, for example, I know that accelerators as EITL, for example, in Europe, which is more software oriented, but so they ask basically they have 5% of the startup and give you some kind of cash. And also give you advices, they organize courses, they present the startup to the investors. So I was wondering, so this is like an example in Europe. So I was wondering in the USA, for example, in Silicon Valley, which is like the horizon in this sense. I mean, because to me, 5% is maybe a big slice, but I don't have any knowledge about the accelerator in the USA. I mean, so this is a question for you.
Well, it depends. Every accelerator is different, but I can say, I mean, Berkeley, it's no secret. They give you 150,000 euros for 6%. I mean, that's the deal. And other accelerators might give you 250,000 for 4%, but all of them have that, some ratio. In Europe, it's just less common. You tend to see, I trained EIT Health. I led a lot of their boot camps. So I know the EIT Health side more than the raw materials side. Now I'm an applicant to the raw materials. But I don't like the model of advice for equity. It's easy to get advice. If you ask enough people, you'll find good people to give you advice. Mm-hmm. If you're shameless and you just go ask 1,000 people, 100 will say yes. I don't believe in giving up equity for advice. But if there's something else, if they can bring you a customer or if they're going to give you cash, then it might be worth it. It's a hard thing to, I don't know if anyone else has experience to share. I mean, Be able who's supporting Molecular Gate is a totally different model of venture capital. I mean, they invest super early and they support people, but they take a huge equity and then they tend to more kind of hire. It's kind of a mixture. It's a hybrid model, I would say, of corporate venturing and venture capital. No, is that fair to say?
So I'm curious about your case, for example, no? So which is the amount of cash that you receive from the accelerator itself, excluding the investors?
It was 145,000 and they took 6%. Okay. 145,000 euros for 6%.
Okay, I didn't get it.
And I think Luminate was similar equity, but for 100,000. And then, Y Combinator, the big ones, I feel like they give you more. I feel like they give you 250,000 maybe for 5 or 4%, something like that.
Which is definitely higher than.
Yeah. So, we needed the cash, so it was a simple decision. Yeah.
Thank you very much.
Yeah.
Thank you. I think there is a question from someone online. Wait, let me see. It's the second one, right? So a question for Karsten. Karsten, do you hear me? It's okay?
Yes, I can.
Okay, so the question is from Pablo Simon. After 15 years optimizing devices and processes around a few specific materials, it is really feasible for Eliatech to move to other semiconductors. How long will it take for a company like yours to introduce a big shift? I guess in the materials that you use for the technology.
Yeah, very important question. So there is always a time lapse between you have a material found in the lab and you have upscaled it chemically and you can introduce it to production. And this is what we account for, let's say, 1.5 year, maybe 2 years. Yeah. This is the time gap you have. That's why you have to be ahead with the research labs in parallel to your production. That's how we calculate internally, and that's how we bring the next generation products to the market. So this means this year we are working on the product preparation for 2027. Yeah, so the 2027 products are this year in the research and development.
Okay.
Is this answering the question?
Probably yes. I don't know if Pablo Simon is happy, but okay. More
Best regards, Pablo.
Some more questions? Okay. Kia, too. So first, Daniel.
I have a question related with patents because I saw that then you have different patents to protect your products, your technology. And I was wondering, so you need to buy the patents in different countries, and what is the selection? So why you decided for those countries, how long you will have the right to use this technology, the durability of patents, so if you could talk about it.
I can start. You choose the countries. So your patent goes first application, no? Then you get granted, then you go to national phases. Well, then you go to international, then you go to national phases. So it takes a lot of years. And then you choose countries that is where you want to sell, basically. So you look into you benchmark your product with your other companies that are selling the same kind of service or product that you want to sell, and you go to that market. And then it's very complicated, and you should have a very good lawyers to help you with that process. But it's normal. It's a normal service. And for example, we have the most complicated national phase we are having in USA. And because we are having a reviewer really kicking ass. But now we changed strategy, and I think it's kind of sorted out after 5 years of national phase. But it's really, it is market positioning, and you just need to know where to sell. And that is based on, this is why you need to select a market. For that, you have to fit your technology, your product to that market. So everything comes together, and it comes a bit more different from the just research. But in parallel, research goes its own way anyway. I don't know if anyone wants to talk about.
Yeah, I would like to add that apart from market, that is the main point, is also you have to consider as well the cost of having a granted patent in a lot of countries, because this is very expensive. And sometimes when you are having a spin-off and when you have few amount of money and you are fighting to get this money, for example, to have a patent in 30 countries is impossible. So you have to think as well on that, and maybe you are getting new patents, new costs. So this is something that you have to have in mind, and in this business plan, which how many money are you able to dedicate to the patents.
Okay. So first of all, thank you all for the nice and inspiring talks. Now I have a question for Lucas. As long as I understood, both you and Molecular Gate are targeting the same market, that is the security and the QR code. So how do you think your technology is competing with Molecular Gate and the reverse? And another question also for you, and it is regarding the commercialization of product that incorporates nanoparticles for everyday use. I think that there are regulations inside the European Union regarding safety and health issue relating to these products. So also if you suppose you have to face this problem regarding safety and health regulation.
Yeah, the first one is, I mean, easier. There is regulation around materials, but we looked into that sort of early on. We haven't registered it formally, but it's not a complex process. It's sort of within the printed ink industry, we're a pigment. In fact, if you say nanoparticles in the ink industry, they get furious because they're like, well, all inks are nanoparticles and they have been for 100 years. So no, so there's really nothing particularly challenging, and the materials we're using aren't unique. I mean, we know Molecular Gate for a long time, and we've talked about this. And I think the first time we met, we were like, "Oh, is this a problem?" And you know, I've seen their deck and I've met their team. It's a very different use case. And the more we talk to customers, the more, at least from our side, we realize, I mean, there's going to be a use case for everything, and it depends on how the customer behaves. So there's going to be cases where a printed ink solution is a better output, or depending on how the reader, you know, using diffused light. I love their solution. And I tell them all the time, if I find a customer where the use case clearly fits, I'm the first one to say, ours is not a good solution for this use case. We have like I think in the first presentation, every technology has a limitation. You have to know yours. There's no point trying to sell something where you know of a better alternative, because they'll figure it out eventually. And so in a market that's 18 billion, we work with them. We work with color sensing, which also sells QR codes with sensors. I mean, there's lots of authentications in Catalonia right now. It's kind of crazy. Redpoints is the best digital authentication solution in the market. That's also a local company. So I see it as a great thing. If customers come to Catalonia to solve their authentication needs, and we can meet it different ways, that's great. I think the other thing is all security packaging, money, passports, again, they have 14 technologies. So 1 can be Molecular Gate, 2 can be distinct, 3 can be color sensing. Like if we can all get onto the same product.
Thank you.
You want?
I mean, just
you've been so quiet.
Well, I'll take it. See, we're standing further apart, but I'll stand next to Luca now so that there's no misunderstanding. I have tremendous respect for this gentleman, and they have truly an A team in Distinct. The only thing I might add, we may have slightly different product types for the market. So in Luca's case, they might have that the bottle over there. In our case, we have the security ink, but it's kind of married to the process as well. So there's a little bit of process involved. And so it's not quite the same business model. So you can sell just the ink, you can sell the ink and process, or you can license IP to high security companies. So we are following slightly different tracks. And yeah, now and then we look at each other and go, Barcelona, our security field here rocks. So.
Okay, thank you all for your talk. I want to ask for the researchers, like how your day-by-day change when you are in academic, because you are come from academics, and you are in a company, because at the end you are in the lab, you are writing projects and this thing. So what do you think is the big change or little change?
I can start with this one, but I actually liked it there before. The really cool thing for me, I'll give you 2. They're kind of personal, so I'm not sure that this is transferable from me to you. One nice thing is that invention is extremely addictive, by far more addictive than cigarettes or what have you. It's really cool when you have a product on the market it's a real high. And so you want to do it again. So it kind of infuses your life with a certain bit of a vector. Even more importantly for me, personally, you don't go to the spin-off for a safe job. So the jokey answer I tell to, my parents when they ask how it's going, I say I feel like a polar bear. The iceberg under me is shrinking, my feet are wet, and it's just the dark ocean to the horizon. You don't go to spin-off for a secure job or for a well-paid job, in my case, presumably in most people's cases. And so people who join spin-offs are nuts. They are really crazy and committed. And what a trip it is to work with people who are in it for real. Not to punch the clock 9 to 5, but to really do something that makes people go, wow, how does that work? So this is the big change. The level of commitment in the team is very different to academia, and it's great. I recommend it.
Oh, well, I work in a company, and the kind of research that you are doing in a company and academia, for me, it's kind of similar, but it's more goal-oriented in a company. You need to deliver a particular product in a particular time. This is what a bit more challenging for me when I started working there. Otherwise, science-wise, I think it's all the same, and the kind of work we are doing here can be it's transferable. You can do similar kind of work in a company also. So yeah, research wise, I don't find any difference, but yeah, maybe you need to follow the deadlines and all these aspects. That's it.
I cannot also. Well, I have a very technical profile, but I have been so I have been a group leader in a technological center for many years, and so I was always on the giving the hand, and helping postdocs or pre-docs coming, and make their transition inside. It's still a research institute, but it's more technological focused, and it's true. Everything. But this is more on the research side. This is more the spin-off feeling. If you are on a pure technical profile, it is. I think the biggest difference is probably time-related stuff. Projects that are shorter in time, 3 months, 2 months instead of 3 years. But if you have national funded projects, it's 3 years still. And then I think another big difference is to work in a multidisciplinary team, that it's probably not so scientific as you will probably, well, people, it's much more, egocentric in the sense that you have your own project to lead. You have colleagues, you can call it multidisciplinary, but it's still very scientific backgrounds, So and then in the companies, then since you have to go to that process on fitting, and then you probably need more engineering, more technology, then you need to interact with you have other inputs and interact with other type of profiles, which is really nice, usually, of course. And when I made my own transition, what I found was that the companies that seem like a big black hole when you're doing your PhD, a company, something like the big company, sometimes it was not scary at all, and it was also motivated and interesting people. It's nice to have people that are motivated and are not just there waiting for the time go by, but there's people everywhere. And for me, it was really exciting to also work and do research with that focus as well, different focus, but also research.
What about with the secret? Because usually when you pass.
Okay,
Yes, inside the companies, yeah, because here in the academic world, usually if someone or a partner or a friend of you asks you for a process, you can offer the recipe of what you do. But I think in the industrial area, you cannot share the recipe of what you are doing. You need, I think this is very difficult for researchers, I think.
This was, I cannot start answering, but I think everybody has, because companies have different perspectives. It's true that in a company, you need to protect your methodology to a certain extent to keep the added value. In my case, for example, I learned very well what I can publish even when I was doing in the technological center, which we already have a lot of secret, let's say. I learned too what you can publish, which is a scientific oriented, and it's different from the technological problem that you are solving and you need to protect. It's completely different. Of course, you need to keep some. I do not agree that, for example, in our company, we do not need to, we are not working on the basis of a deep secret. Everybody knows there's a big transparency. Other companies are not like that. This is what I said. You can explain stuff without commit your developments, but it's also a strategy. I mean, I don't know, the different perspectives. Somebody wants to add? Okay.
Yeah. So, I mean, when you are developing a process or a technology, there are some parts you are supposed to keep it as a secret, but if I wanted to communicate among our teams, there are other parts like, okay, maybe I don't need to go to the details, but I still can explain, okay, what is happening, what's the result, without explaining the exact parameters of something. So, but still, yeah, if you are continuing pursuing your research and everything, develop technology to the market, you still need to, yeah, keep the secret and do the confidentiality stuff. I think even when you are applying for patents, this applies. So even in academia, this can be happening, right? Yeah. So this is what I understood from the patent point of view. So yeah.
More questions?
So I have a question for Alexander. So which is your goal? I mean, so do you really want to go to market, or because I mean, I understand that you are like in the stage of research, no, investigation. So you are working in the lab at ICMAB, right? So if you want to go to market, do you think these labs are enough to reach this goal, or you need maybe new facilities? And in this case, the question is, CSIC would allow the spin-off to have its own facilities or not? And maybe, yeah, this depends on which is your goal, because I know also that CSIC, another thing that that CSIC do is that they also sell licenses and patents to other companies, right? So this is another possibility also. But I didn't understand if you have patented the technology or not. So.
Well, you're the next CEO. These are such good questions to ask. Okay, so regarding incubation, in the end, we are a very small outfit. There's three of us, including the CEO that is not based at ICMAB. So for incubation, you kind of choose where to spend your money, and we'd rather spend the money on people and traveling to, knock on doors, and eventually they start to open. But soon enough, for the next level, and we are just standing on the precipice of that step, you would need to get bigger equipment, and then you choose where to be incubated. One choice is to slime up to CSIC, and well, Alfonso might help us with that. Another option is to be incubated in the potential end user of this stuff. So we are looking for that, and I kind of like that option more. Ideally, it's in a nice country as well, or in a nice place. So this is the first question. And I forgot all the others because I was so excited to answer this one. Can you remind me the part two? Yeah, right. So the patenting is kind of tricky. So the whole molecular gate, multi-layer, basically tracing paper concept is patented. The patent is granted, and it's protected in a bunch of countries, in Asia and in Europe. And this one covers something like what I showed at the end with the self-aligned doping concepts. So all of this is part of the patent. Now we're tidying up the patent for the time temperature indicators, which will be also a shared patent with the SIG because of Mariano's involvement and huge contribution. And then for security, Luca would be the better guy to answer this. Security, I mean, patent means open or disclosed. It's kind of crazy to patent security features. So you can try to pattern not quite the final product, or you can file a trade secret. And this is what we're doing right now. Right, yeah. Yeah, you can think of it like this, yeah. Mm-hmm. Mm-hmm. Yeah, the aim of the spin-off is to, well, I guess to be sold. Case, yeah, we're a young outfit, and I'm a dreamer. So there's the CEO who would dots the I's and crosses the T's. He would be the right person to answer this. In our case, being sold is okay, but to build up value for the company, what in my naive understanding of these things, to be sold for a lot of money, you need IP and people and stuff, you know, physical stuff, not just dreams, schemes and themes. And so these things are quite far down the line for us. Before that, I'm pretty sure we'll go to market first with, well, any of the 3 product types that I showed, and then further down the line, we can keep in touch and I'll tell you how it happens.
Just a very brief addition. If you sell a company before it has any revenue, it's going to be worth a lot less. So someone might buy it for 100,000 or 300,000. So it's all about value optimization. The further you get, the more valuable you are. It's a game of, and this goes all the way up to billion-dollar companies. So it starts here. What is the motivation of the founders? Is it to sell for 500,000 or 100,000, 10 million, 20 million? This is a very, very important conversation for the founding team to have when you start. It's hard to agree on. Even Alex and I have different visions. There's ways to manage that, but you need to talk about it a lot.
Yeah, well, you have to consider that the spin-off is an independent entity from CSIC. And what CSIC does is it allows the company to be inside CSIC facilities, but not forever. It's something temporary for the first years, so that it makes it easier for the company not to pay rent or to all these kind of things. So it helps in that way to the company. But the company has to leave sooner or later CSIC facilities and go to another facilities, and that's, well, they have to look for some facilities and so on. And something that you said that it's important to remark that we don't sell patents. We license patents. We keep the ownership. We don't give the ownership to other to third parties or to spin-offs. It doesn't matter, because we always keep the ownership. That's the reason why is because if imagine the company at the end it has no future, or the company is doing things that we consider that are not the things that we want them to do, we can final this agreement, and the patent is still from us. And obviously, we can license patents to already established companies. Sometimes it's the best option. Sometimes the best option is to create a spin-off and develop the technology, and then try to sell this company to an already established company that is in the market. It depends. So we decide it's a rent. License is a rent. Yeah.
More questions? Because if not, we will close the session. I think it was already quite long. So you know the speakers are, most of them, they are around, so you can always contact them. I think you had here a good opportunity to see different cases, different spin-offs, companies in different process of development. Karsten is still connected. So you saw the case of Eliatech, so very successful company, so it's very interesting. Karsten, thank you for being here. So please thank all the speakers that we're having here today. So we thank you. And I would like, and also I would like to thank you all connected online or being here in the room for your presence and your interest. Okay, bye.
Yeah. Thank you. Bye-bye.